Now let's take a look at some higher order derivatives. So we talked previously about how we could find the position function, which is s of t. And then if we derived the position function, we would arrive at the velocity function, because essentially we're saying what is the change in position with respect to time, which is velocity. Now we're saying, what if we took the derivative of the velocity function? So what is the change in velocity with respect to time, which is acceleration? Well, how do I get to the derivative of velocity? I'm taking s of t, the second derivative. So notice double prime here because I'm taking the second derivative. And so if I want to find acceleration, how velocity is changing with respect to time, I simply derive the velocity function. So again, the second derivative, s double prime t, is called a higher order derivative, so I could find the third derivative or the fourth or the fifth, etc. And I've just given you some different ways that you might see it written. They all should look familiar to you because we've seen the first derivatives before, but now you can see where those second or third or fourth or fifth values would go. So here's a great example for us to look at together. So in 1971, David Scott demonstrated the fact that the moon has no atmosphere by dropping a hammer and a feather and showing that they fell at the same rate on the moon. So even though on Earth, obviously the hammer would fall much more quickly than the feather, on the moon, because it has no atmosphere, that is not the case. So they've given us the position function for those objects and also graphed it here, and obviously we're looking at a height of 2 from which we are dropping these objects. So what we're trying to solve here, it says what is the ratio of the Earth's gravitational force to the moon's? So what we don't know is we need to know the moon's acceleration due to gravity. Because we know the Earth's acceleration due to gravity is 32 feet per second squared, or 9.8 meters per second squared. So depending on if we're looking at meters or feet, and I believe in this case we're looking at meters, we're going to be comparing in a ratio to whatever we determine here. Now keep in mind we're looking for acceleration due to gravity. So if this is position function, I know if I derive this once, that's going to give me the velocity, and if I derive it twice, that's going to give me acceleration. So that's what I'm going to be doing with this function. So again, here let's take a look. We have the acceleration is the differentiated twice position function. So I took this function, I differentiated it once, took the 2 times the negative 0.81, then times t to the first, and then obviously the derivative of 2 was 0. Then I took the derivative of negative 1.62t, which is just negative 1.62. So s double prime of t, which is the acceleration function, is negative 1.62. So what does that mean? That on the moon, the acceleration due to gravity is negative 1.62 meters per second squared. These should both be squared. On the Earth, because we're dealing again with meters, we're going to use the 9.8 meters per second squared. And again, since it's acceleration due to gravity, these would both be negative because they would both be moving towards the Earth or the moon. So the ratio would be 9.8, which is Earth, over negative 1.62, which is moon. As I divide those, I get about 6. So the ratio of the Earth's gravitational force to the moon's is about 6. Here's a great question for you to ponder for a little while, and we haven't looked at these at all. But I really like questions like this because it makes sure that you understand what a derivative actually is. So remember, the derivative is a new function, and the new function is always 1 degree less than the original. So if I said my original function, let's say, was f of x equals x to the fourth plus 3x squared, you would say, all right, well, the derivative of that function is 4x cubed plus 6x, and the second derivative would be, again, 1 degree less than that, so 12x squared plus 6. We can see that I started at 4, the derivative is 3, the second derivative is 2. So hopefully that can help you to, quickly find which would be the original function, which would be the first derivative, and which would be the second. So press pause, try that question, then press play to see if you are correct. So again, what I'm looking at here is it looks like function 1 is a parabola. So this is going to be an x squared function. And we don't know what all of the other parts are, and we don't need to. It could just be y equals x squared. Function 2 is a linear function. It's a line, which means it's y equals mx plus b, so it's x to the first. So I'm really only caring about the degrees here. This guy, hopefully you recognize as a cubic function. Oops, put the 3 in the wrong place. X cubed. And again, I'm not worried about what numbers go in front. I'm not worried about what numbers go in the back, etc. I don't care about any of that. I'm really just looking for what would be the only thing that makes sense. So f of x must be 3 because it's a cubic function. And then if I took the derivative of a cubic function, I would get a squared function, so that has to be graph 1 for f prime of x. The derivative of a quadratic function would be a linear function, so that has to be graph 2 for f double prime of x.